Next talk is going to be by Dr. Caryl Gronwall, who is a research professor here at Penn State, and she's going to tell us about the HETDEX project and how HETDEX and Penn State are trying to discover dark energy. So here is Caryl.
HETDEX at Penn State.
Not so much. Okay, so I wanted to talk to you today about how we're going to use the Hobby-Eberly Telescope, which is a 11-meter telescope in West Texas at McDonald Observatory. It's this dome here. This picture was taken 5 years ago. The wildfires got very close. They did not get to the telescope thanks to the heroic efforts. What? A little closer? Is that good? Okay. So they did not get to the dome. So first of all, what is dark energy? So I'm going to do some background first. We understand physics very well. Spectra of objects back to 95% of the way back to the Big Bang. The universe is about 13.5 billion years old. We observe the spectra of objects. We see emission lines and absorption lines due to atomic and molecular transitions. They look the same as they do on Earth. We understand electromagnetic forces. Similarly, we see thermonuclear explosions, massive stars go supernovae. We see supernovae back to 75% of the way back to the Big Bang. Those thermonuclear explosions look like thermonuclear explosions that we see locally. We understand the strong and weak forces. We understand physics. Similarly, we understand the laws of gravity that haven't changed over the history of the universe. So we see the images here are gravitational lenses. So Einstein's theory of general relativity says mass bends light. If you have a massive galaxy, this ring is from a galaxy behind the massive galaxy in the middle. The mass from that galaxy has bent. The more nearby galaxy has bent the light from the more distant galaxy, created the ring. Similarly here, we have a massive cluster of galaxies, lots of galaxies, all these red objects are galaxies in the cluster. You see arcs from more distant galaxies bent. So light from the galaxy, mass bends space. That's what Einstein tells us bends the light. We see that on Earth. So we understand physics back very early on in the universe. But what is the universe made of? If you had asked an astronomer 50, 60 years ago, most astronomers, Fred Hoyle, if you had asked Fred Hoyle 50 or 60 years ago what the universe was made of, he or she would have told you that the universe is made of things like we are made of. I'm going to use the term baryons several times in this talk. So baryons, what we're made of, protons, electrons, neutrons, things that we see on Earth. Now, our current understanding of the composition of the universe is that what we're made of, this little chunk here, baryons, is only a small fraction of the total energy budget of the universe. All of the mass of the universe, this chunk here, about 25%. About 5% of it's baryons, stuff we're made out of. Most of it's dark matter. So all this mass bending light is mostly dark matter. It's stuff we don't see. Dark matter, no electromagnetic radiation. And no, I don't know what dark matter is, and neither does anybody else. People are spending a lot of time looking for it. The largest portion of the energy budget of the universe, and this was just discovered about 20 years ago. The first discovery was in 1998. Dark energy, 75% of the energy budget of the universe is dark energy. That means it's not any of that physics that I talked about. It's not gravity, not electromagnetic, it's not strong and weak forces. It's something else going on that we don't understand. So how can we trace dark energy to try to understand it better? So first of all, what is the universe made of? Baryons, stuff we're made of. Protons, neutrons, electrons. They interact with other baryons gravitationally. They also interact electromagnetically with light, with electromagnetic radiation. There's neutrinos. Neutrinos are very, very, very low mass particles. They don't interact very much with anything because they're so low mass. We don't know what dark matter is. Dark matter does not interact with electromagnetic radiation, with light. It interacts with baryons, the stuff we're made of, only gravitationally. And it probably doesn't interact with itself except gravitationally. It's probably the dark matter particles are probably fairly massive. So neutrinos are low mass. EV is a unit of energy. Mass is energy from Einstein, so electron volts. Neutrinos are pretty light, less than 0.3 eV. Electrons, half an MeV. Protons, 900 MeV. Dark matter, probably giga electron volts. Okay, but I'm caring right now about dark energy. So how do we trace dark energy? We know that the universe is expanding. The first person to discover that was Edwin Hubble back in the 1920s. So this was less than 90 years ago that we discovered that the universe was expanding and figured out that there was, in fact, a Big Bang at the beginning of the universe. So we know physics of the universe has not changed. Gravity, electromagnetic radiation, strong and weak forces, those seem to work pretty much the same as we go back in time. Universe is expanding. As the universe is expanding, things are moving. The space between the universe is expanding. Galaxies are getting further and further apart. A good analogy for this is raisins in a loaf of bread. As the bread rises, the raisins get further and further apart because the dough is rising. Same thing with the universe. Started out as an infinitely dense point, hot, dense point. Universe expands, gets bigger and bigger. Galaxies get further and further apart. We know what physics is like now. We can infer what was going on then in the early universe. So, inference. Universe was very small, or very early on. Everything was very hot and dense. So hot means everything's moving fast, high temperature, high pressure. So that's what the ideal gas law tells us, for those of you who've taken some chemistry. Universe is pretty hot. Any particles of gas, baryons, are ionized. So the electrons and the protons are pulled apart. Ionized material has a charge, electrons and protons. They interact electromagnetically with photons, with light. Light is continually absorbed and re-emitted, it's scattered. So early on in the universe, electromagnetic radiation, light is coupled to the baryons, the stuff you and I are made out of, gas. Denser is the gas, everything's closer together. Those photons, that electromagnetic radiation cannot go very far before it interacts with another charged particle. Universe is expanding. So those particles are going to get further and further away from each other. And as the universe expands, it's also cooling. It's less dense, less pressure, the temperature goes down. So the protons and the neutrons start to combine with one another. The terminology that astronomers use is recombination, which is a bit of a misnomer because they were not never combined early on in the universe to begin with because it was too hot. That means the photons decouple from the electrons and the protons. They start to escape. The other thing that's going on is you have that pressure. There's pressure from the photons being coupled to the electrons and the protons, and you had a pressure wave, a sound wave, an acoustic wave. I'm going to use the word acoustic oscillation. So after all of the neutrons and the protons combine to form the nuclei of atoms, light can escape. So the universe becomes transparent. So this is as far back as we can see to the beginning of the universe, is the epoch of recombination that happens about 380,000 years after the Big Bang. And that's what we observe when we're observing the cosmic microwave background radiation. That light has cooled as the universe is expanding, and we're seeing black body radiation corresponding to a temperature of 3 degrees Kelvin. So everything with the temperature gives off a light. I give off light, the TV gives off light. Anything with the temperature gives off light with a characteristic black body spectrum. This is frequency, so frequency of light versus how strong it is. Something that is hotter will give off more light. In the ultraviolet, something that's cooler will give off more light. In the infrared, this is very cool. This is very long wavelength light. It's the same thing if you got any of you who are old enough to remember old black and white TVs, the noise, that's some of that noise is coming from cosmic microwave background radiation. The cosmic microwave background radiation was actually discovered by two physicists, Penzias and Wilson, working at Bell Labs in New Jersey, and they were doing a radio antenna experiment, and they had noise they couldn't understand in the radio antenna. They went to all the trouble of cleaning the pigeon poop out of the radio antenna. It turned out what they were seeing was the remnants of the cosmic microwave background. This flat here is the black body radiation discovered by the Hobby satellite in the mid-1990s. And it's very, very, very close to a black body radiation with corresponding to a temperature of 2.728 Kelvin. That directly matches predictions, and those error bars are blown up by 400 times. So very, very accurate. All right, so I talked about, we've got, before recombination, we have photons coupled to baryons, to electrons and neutrons. They're causing a pressure wave. We've also got dark matter in there. So, but the dark matter is decoupled from the electrons, from the baryons and the photons, and you end up with two peaks in the early universe. The middle one is due to the dark matter. That wave that goes outwards is our coupled photons and baryons, so photons and electrons and protons, and so you end up with this characteristic acoustic wave. It's just like particle of sound moving through air, same thing, moving through this plasma of gas and light. First, middle peak is dark matter. This outer ring is our acoustic wave, baryonic acoustic wave. So what if we had a bunch of little micro density fluctuations in the early universe? They will grow with each other. So you're going to have individual fluctuations. They'll grow. Some of them might overlap. You'll have some high density regions. You'll have some low density regions. And this is in fact what we see when we observe the cosmic microwave background today. This image was taken from the Wilkinson Microwave Anisotropy Probe satellite about 10 years ago. Much higher resolution than the COBE data from 20 years ago. And this is a temperature map looking out on the sky all around us. The different colors correspond to slight temperature differentials from a nominal 2.728 degrees Kelvin. These are very tiny temperature fluctuations. They're 1 part in 10 to the 5, and those very tiny temperature fluctuations correspond to very tiny density fluctuations at recombination, so 380,000 years after the Big Bang. We see these density fluctuations in the microwave background, and these density fluctuations are what grow up to be galaxies and clusters of galaxies and superclusters of galaxies, and the large-scale structure of the universe that we see today grew out of these tiny little 1 part in 10 to the 5 density fluctuation in the early universe. So we have 2 things we want to measure if we're trying to understand how the universe evolves with time. In particular, we're focused on dark energy. So first thing, the universe is expanding. How fast is it expanding? This is my one and only equation. Kate had an equation, I get one equation. The rate at which the universe is expanding is called the Hubble constant. It's, again, a bit of a misnomer because the constant has changed over the history of the universe. It slowed down originally due to Big Bang started everything off. The universe is expanding. Hubble constant will decelerate, slow down, and then it accelerates due to dark energy. So dark energy is basically an anti-gravity term to the expansion history of the universe. And right now we're at a point in time where the expansion history of the universe is going from slowing down to speeding up, from decelerating to accelerating due to dark energy. So we want to measure how fast the universe is expanding. So the Hubble constant H, which is a function of time, Z stands for redshift, which is how astronomers measure time. Don't worry about it. How fast, if we're any little dot, we're one of these galaxies. Every galaxy is moving away from us as the universe expands, and galaxies that are further away from us are moving away from us faster. So we need to know V equals the Hubble constant times how far away it is. So we need to know how fast it's moving away from us. That's pretty straightforward to measure. We can use something called the Doppler shift, and how far away the galaxy is. Second thing we want to know is how much dark energy is there and how does it change with time. So those tiny little baryonic acoustic oscillations, BAO, we see them imprinted on the structure of the CMB. That's a standard ruler. We also see it when we measure the correlation length, basically how galaxies are clustered today. So we can use it as a standard ruler to measure this characteristic angular distance between high density and low density regions between galaxies. Early on, we can use the CMB. The Hobby-Eberly Telescope experiment that I'm going to talk about today is doing it sort of in the middle, and that we've done it nearby with the Sloan Digital Sky Survey, which is what every little dot in there is a galaxy, and you can see that there's structure to that, and the size of that structure is correlated to those same acoustic peaks from the CMB. So we want to trace the expansion history of the universe and how much dark energy there is, and is it changing with time. So this is again, what has been measured locally with the Sloan Digital Sky Survey, which is another. The Hobby-Eberly Telescope in West Texas, the HET. Our project is called the Hobby-Eberly Telescope Dark Energy Experiment, HETDEX. The HET is owned by the University of Texas, the Pennsylvania State University, and several universities in Germany. And we've, for this project, we've also got some contributors from a few other institutions, Oxford, Texas A&M. We're going to use this telescope to map out the large-scale structure of the universe about 10 to 11 billion years ago. So how are we going to do that? First thing we did was we had to totally rip apart. This is the bottom of our primary mirror of our telescope. We put on a new secondary top end to increase the field of view of the telescope, get a much wider field of view. And then what we do is we're filling the field of view of our instrument with fiber bundles. Each little fiber, think of a little fiber cable, feeds the light to a spectrograph. So we have 78 fibers per bundle. Each of these green squares is a bundle. Those 78 fiber bundles are attached to 156 spectrographs. The spectrographs are heavy, so the lights go down through these tubes. All of those fibers get fed through a tube into spectrographs that are down here on the side of the telescope. That allows us to take spectra of pretty much anywhere in the sky that we're pointing simultaneously. The instrument is called VIRUS. Help me out here, Robin. What's the acronym for VIRUS?
Visible, replicable unit spectrograph, something like that.
Anyway. So we're basically replicating the spectrograph a bunch of times. The integral field unit, we've got a bunch of these fibers put together. That's what that means. Our wavelength range is 3,500 to 5,500 angstroms. That's in the blue visible. We've got a bunch of clones of this. Each little dot, this is a picture of the actual instrument, is a bundle. So any pointing, we're going to get 34,000, not 35,000 spectra per pointing, per observation. What we're going to do is we're going to map out an area of the sky. This is our survey region here in red. That corresponds to 420 square degrees total. It's going to be a 3-year survey. We have just recently started taking commissioning data within the last 6 months or so. So the survey will start for real any day now.
Tomorrow.
Tomorrow.
No, next day. Next day.
Soon, very soon. We're going to take that. Really interesting part of this survey is that we don't point. We don't look for a galaxy and then put a spectrograph on it and take its spectrum. We just take spectra of whatever we get. That emission line that we're focused on in galaxies is called the Lyman alpha emission line. It's the N equals 2 to 1 transition to hydrogen, for those of you who are familiar with the Bohr atom. So we're going to take 35,000 spectra at a time, fill in the gaps. We're going to get lots and lots of spectra. This plot is a bunch of different surveys. Don't worry about the names. Density of spectra, number of galaxy spectra per square degree as a function of the area of the survey. So if you have a smaller area, you can get a lot higher density spectra. Larger area, lower density number of spectra. So where does HETDEX fall on this? It's up here. Whoa. But HETDEX is a blind survey. That means we're not pointing at galaxies. That means most of our fibers end up on blank sky. So if you actually count where the galaxy spectra that land on galaxies, we're going to be up here. Still above most surveys in terms of density versus area. When we do hit a galaxy, and we will quite frequently, HETDEX will see its spectra. As I said, we're aiming for Lyman alpha, the n equals 2-to-1 transition of hydrogen. That rest frame of that line is 1216 angstroms. That gets redshifted into our 3500 to 5500 angstrom regime at redshifts z equals 1.9 to 3.5. To translate to that back to you, that's between 10 and 11.7 billion years back in time. The universe is approximately 13.5 billion years old. So we're going pretty far back. And as I said, we're doing commissioning now. We are finding Lyman alpha emitters. My colleague over here, Professor Jiang, found the first Lyman alpha emitter in the commissioning data. So, strong emission lines. Not much else. When a Lyman alpha emission line galaxy, all you're going to see is one single emission line. Part of the reason we're going after Lyman alpha emission line galaxies is they're really easy to pick out in short exposure time. And we're still in the process of refining our software to do this automatically so that Donghui doesn't have to look at them all by hand. And the reason we don't want the Donghui to have to look at them all by hand is that we expect to find about 800,000 to 1 million Lyman alpha emitters in that redshift range between 10 to 11.5 billion years ago. We're also going to find about 1 million more nearby galaxies via their oxygen 2 3727 line, so that's within about the last 5 billion years. 400,000 other galaxies, stars, clusters of galaxies, quasars like Kate was talking about, asteroids, supernovae. So there's a whole bunch of ancillary science that we can do, but our main goal is to trace the expansion history of the universe, any evolution of dark energy with time by mapping out the large-scale structure of the universe at redshift of 3 about 11 billion years ago using those Lyman alpha emitting galaxies. So when we do that, we'll be able to measure how much dark energy there is at redshifts greater than 2, so more than 10 billion years ago, back to the Big Bang. Measure the curvature of the universe to about 1 part in 10 to the 3. Measure the Hubble constant to about 1%. Measure the evolution of dark energy. And this plot here is showing our percent accuracy on the Hubble constant versus redshift, and we're in a very sweet spot compared to these are other surveys aimed at measuring the same thing. So I don't have any results to show you. This is more of an advertisement. So assuming Astronomy on Tap is still happening 3 years from now, I can come back and give you an update. Thank you very much.
I have a question. You might have said this, and I'm sorry. What is the characteristic scale of the BAO at z equals 2?
What is the characteristic? What it is?
Well,
He knows. Wait, repeat the question and then answer.
So he's asking what's the characteristic scale of BAO in redshift 2. The co-moving scale is 100 megaparsec. Redshift 2 you divide by 3, and 30 megaparsec in physical scale.
Thank you.
Does dark energy have anything to do with this theoretical vacuum energy?
So the question is, does dark energy have anything to do with the theoretical vacuum energy? So the vacuum energy is antimatter and matter annihilating one another, and in fact that would cause the same sort of anti-gravity pressure term, but when you calculate the order of magnitude, it's off by a factor of about 10 to the 120, so it does not work. But people have considered that.
So where are you storing all the data?
Where are we storing all the data? All the data is being stored at the Texas Advanced Computing Center at the University of Texas, Austin. And it does, in fact, require a fair amount of disk space, yes. And processing power, we're doing all of our software running on there as well.
So I have a quick question. So you look for this Lyman alpha emission line, but all you see is this one line. So how do you know that it is Lyman alpha?
It's a fine question. Which no. I got this one. This one is me. I've in fact spent the last decade of my life worrying about this question, doing other surveys for Lyman alpha emitters. So you are quite correct. You have one line. Oops. That will do. You have a single line. What it's telling is what's called the equivalent width of the galaxy, so how bright the line is above the continuum. So basically there are two main things it can be. It will either be Lyman alpha at a redshift from 2 to 3.5, or it will be oxygen 2 at a redshift less than 0.5, and those have characteristic line strengths relative to the continuum, such that if the stronger line versus continuum ones have a much higher probability to be Lyman alpha. I can't tell you 100% that it's Lyman alpha, but I can give you a good estimate of the probability that it's Lyman alpha.
And if she's making a mistake, Henry can tell you how bad the mistake is.
If I screw it up, that's Henry's thesis.
All right, let's thank Caryl one more time.